Good evening, ladies and gentlemen. My name is Alexander Burtsev. I'm from Southwest State University, and the theme of my presentation is the mathematical model of automated control of heat flows in the supply and exhaust ventilation system. Abstract. The aim is to study a mathematical model of optimal control of heat flows of supply and exhaust ventilation systems with built-in integrated heat exchanger-recuperator. To achieve these goals, the methods of mathematical modeling and the certain of a computational model were used in the work. Introduction. In modern ventilation and air conditioning systems, one of the main components is an automatic control system, ACS, which performs various functions and also provides highly efficient operation in the range from shutdown functions to centralized regulation and control of climatic parameters, temperature, humidity, control of concentration of hazards, and the air velocity. The developed mathematical model, which is based on the principle of feedback regulation of process by obtaining information from external sensors-based mathematical modeling of physical processes, acquiring in a serviced building of structure provides prediction of thermal and ventilation parameters of the system in real time with low response time and consuming power costs, creating a comfortable and healthy indoor environment. Materials and methods. Exhaust air removed from room is used a heating medium. At the same time, the system is controlled with an independent connection scheme to the heat supply system. The air heat in the room is a consideration as an incompressible gas. The heat exchange between the heating and heated heat carriers is a stationary process. The turbulence of heating and heated coolant flows is isotropic. The schematic diagram of the supply and exhaust mechanical ventilation system with ACS is shown in the picture 1. You can see it on this slide. Materials and methods. The experimental supply and exhaust system under study with a plate heat exchange-recuperator ventilation system operating in a quasi-stationary heat transfer mode is shown on figure 2. Here is the figure 2. Results. The transferred amount of heat is determined by the formula W. When installing the valve V1 and the supply fan M1, figure 1, 2, 3, between the supply and exhaust ducts of the ventilation systems is accordance with the requirements, the air consumption G1, Gm, and the mixing coefficient of point A of hot and cold and air masses U should be taken into account. It is important to note that the airflow in the quasi-stationary modes has a directly proportional dependence on the heat flows, where the temperatures T1 and T2 are taking in the range of 15 to 65 degrees. At the same time, it can be assumed that the specific heat capacities at constant pressure C1 and C by N are equal to 1.005 kilojoules by kilogram degrees Celsius. G1, G2, and G by A, respectively, the airflow in the supply and exhaust ducts, kilograms by G by M airflow through the support fan M1 and point A. The specified agreement is made taking into account the mixing coefficient U. The heated coolant passes through the adjustable flap V1 with a fractional of the opening key 1. Then the flow using the supply fan M1 with the thermal load R, functioning with the fraction of the full capacity Kn. Then the valves of the heat flows Q1A, Qmi at point A can be determined by the formals. The heat flow of a ventilation room with heat R has temperature T int 293 K. In the quasi-stationary mode, the QK flows is transmit through the wall of the heat exchange recuperator, while the equation will have the form: the temperature of the supply air in the room F, the area of the inner surface of the recuperator M2, you can see here. Well, we will consider the coordinated operation of the valve V and the supply fan M1 respectively of their liner sections MNPL figure 3 and figure 2. The ventilation process in the normal mode stationary over time, the valves of the main parameters do not change. Based on these factors, the heat balance equation must be taken into account. As a result, we get the balance at point 1. Let's introduce the notation. Graphically, the dependence is presented in figure 5 as a family of curves 1, 2, and 3, and the figure 5 you can see here. The coefficients Km and K1 from expressions are inversely proportional. You can see it. Let's analyze the operation of the circuit in figure 2 based on the heat balance equation, and we will assume that the violation of the temperature pressures if there's are no internal sources of heat cold in a ventilation room with a thermal load R occurs due to a change the temperature of the outside air taxed by certain amount delta taxed. Such dynamics respectively leads to a change in the temperature of the T int. Let's assume that the temperature of the supply air Tx has increased by Tx degrees, which with the position K1 and Km unchanged will lead to an increase in the temperature in the room R by the value of delta T int degrees. In this case, to restore the thermal balance, it is sufficient to increase the proportion of Km of the full capacity of the supply fan M1 by the value of delta Km and accordingly reduce the proportion of K1 of the full capacity of the valve V1 by the valve of delta K1. consider the option of ventilation with minimal energy consumption while maintaining the normal temperature of T int, taking into account the expressions and the given temperature difference. We investigate the function for a local X terminal. Differentiate expressions. You can see here, and we define critical positions of the first kind. If we consider that K1 is more than 0, then should leave this. Here is the graphics. Consider condition for determining the local exterium, and figure 7 is definition of dependency of the half interior. Conclusions. As a result of the work carried out, a mathematical model of heat flow control is the supply exhaust ventilation system with a built-in integrated heat exchanger recuperator is proposed and investigated. The optimal values of the consumed thermal energy and the parameters of the ventilation system separation are obtained. The developed mathematical model, which is based on the principle of feedback process regulation by obtaining information from external sensors based on mathematical modeling of physical processes occurring in a serviced building of structure, provides real time for staining of thermal and ventilation parameters of the system with a low response time and computing power costs, creating a comfortable and healthy indoor environment. Thank you for your attention.